In the last class, we did calculations, thrust calculations and fuel flow rate calculations for a turbofan engine. Let us summarize what we have done so far for this problem. We looked at two operating conditions. One was static test stand condition, in which we calculated the total thrust T of the engine to be 229 kilonewtons, and we calculated the mass flow rate of fuel mf dot to be 2.64 kg per second, which corresponded to a TSFC of 0.0414 kg per hour Newton, and we compared with the manufacturer's manufacturer quoted value for this. This was 233.6 kilonewton for the total thrust, and for the TSFC the manufacturer quoted value is 0.03781. So the values seem to compare reasonably well, and based on this we calculated the area of the cold nozzle to be 1.5 meter square, and we calculated the area of the hot nozzle to be 0.511 meter square. So this were done for the static conditions. Then we moved on to cruise conditions. And for the cruise condition, our initial calculations, let me also add one more thing here. We assumed the mass flow rate for this case to be, it was given to be 670 kilogram per second, and the turbine entry temperature was given to be 1500 Kelvin. Now for cruise, we assumed same mass flow rate, and we calculated the thrust to be total thrust to be 132.79 kilonewton, which compares very poorly with the manufacturer quoted value of 51.41 kilonewton. And the mass flow rate of fuel in this case was calculated to be mf dot was 0.08 kg per hour Newton, and the TSFC, I am sorry, mass flow rate. So the TSFC is 0.08 kg per hour Newton, and the mass flow rate of fuel was calculated to be 2.94 kg per second, and the manufacturer quoted value for this is 0.0642. So the comparison for TSFC is also quite poor, and we calculated the areas of the nozzle for the same mass flow rate. When we did the calculation for the areas, we obtained the areas to be 3.661 meter square, and the hot nozzle area to be 0.8855 meter square for the same mass flow rate. So we once again took the mass flow rate to be 670 kg per second, and we took T04 to be 1500 Kelvin. And we concluded quite rightly that this is the source of the discrepancy. This is what is causing the discrepancy. The area of the nozzle in a commercial turbofan engine has to remain the same. It is not a variable area nozzle. So what we can do, the first thing that we can do is try to adjust the mass flow rate. Now what you must remember is, if I change the mass flow rate, how many of the quantities that I have calculated is going to change. Remember, we said we finally wanted to evaluate the exit static pressure and the exit velocity. These are the two quantities that are used for calculating the thrust, right? So these are the two quantities that are used for calculating thrust. So if I change the mass flow rate, will these quantities change? Now if you go back and look at your calculation procedure, you will notice that evaluation of any of the thermodynamic state properties, stagnation pressure, stagnation temperature, static pressure or velocity, did not involve use of any mass flow rate. We used the bypass ratio but not the mass flow rate. So as long as you do not change the bypass ratio or T04 or any of the thermodynamic properties, we can actually quite freely change the mass flow rate of the that is passing through the engine. Right? So we can adjust. So there are two things that we can do. The first thing that we are going to do is adjust mass flow rate. So I can adjust this without changing my PE or VE. Both should remain the same. So if I do that, now what I need to do is passing this mass flow rate through the nozzle under cruise conditions require this kind of area. What if the area available is only 1.5 meter square? What should the mass flow rate be? That is how we scale this, and we scaled it yesterday. We saw that the scaling factor is going to be for m dot should be 3.661 meter square divided by 1.5 meter square, which gives me 2.441. So m dot now has to be adjusted to 670 kg per second divided by 2.441, which gives me 274.48 kg per second. So the mass flow rate has to be reduced from 670 kilogram per second to approximately 274 kilogram per second. Okay, questions? Yes?
As we are changing area, it will also change choking condition. It will also change upstream conditions.
How will it change upstream condition? That is why I said before I started this, I told you that we did not use the mass flow rate in the calculation of any of the thermodynamic state properties. P01, T01, P02, you can go back and check your calculation. You will notice that we have used the bypass ratio, but not the actual value of the mass flow rate itself. Okay? So I can freely change mass flow rate without changing PE or VE. That is permitted. Even if you change AE, remember my velocity is the same. Right? Velocity is the same. So now I am passing less mass flow rate through this. Stagnation pressure remains the same. Correct? Stagnation pressure remains the same. So my thrust is going to be scaled accordingly. The thrust we have to recalculate now. Okay? What you are saying is true for the thrust, but thrust uses mass flow rate. So all I am saying is the VE will not change, but other quantities will change. For example, thrust will change, fuel flow rate may also change. Fuel flow rate will definitely change. Correct?
So as intake is same and exit is changed, means mass flow rate is inlet mass is same.
No, what I am saying is the compressor should run at a speed which is such that it takes in only this much mass. Okay? So you throttle down the engine, so the compressor RPM goes down, fan RPM goes down, so the mass flow rate that goes through the engine also goes down. Okay? So an engine does not always operate at the same mass flow rate. Mass flow rate through the engine can be changed by adjusting the speed of the compressor and fan. That is quite possible. That is what we are proposing here, that the engine should take in less mass flow rate.
But engine is cruising at same speed, na?
Correct. The engine is cruising at the same altitude. VA is the same. VA is the same. But if you go back and check your calculation, you will notice that this was calculated without using m dot. That is the most important point. These two quantities were calculated without using m dot. So when I change m dot, these two will remain the same. There are no issues. Okay? So this then tells me that AEC now will revert back to its. So for the adjusted mass flow rate and for the exit velocity we have calculated VEC, the area of the cold nozzle can now be 1.5 meter square. There is no problem. Now we have to see what the area of the hot nozzle is for the new mass flow rate. So we have changed the mass flow rate like this. So m dot h is going to be, the mass flow rate through the hot nozzle is going to be 1 over b plus 1 times m dot, and if I substitute this value for m dot, I get this to be 51.69 kg per second. So this is the mass flow rate now through the hot nozzle. Okay. So for the calculated value of VEH, what is the area that is required to pass this mass flow rate? So AEH now can be calculated, right. So AEH is going to be m dot h divided by rho EH times VEH, and if I substitute the numbers, I get this area to be 0.363 meter square. Whereas the desired value for the hot nozzle area is 0.511 meter square. Okay. Now I cannot play this same trick again. If I adjust the mass flow rate now, the mass flow rate through the cold nozzle will also change. So this can be done only once. Okay. So I need to adjust something else to take this effect into account. How do I adjust the condition so that the required amount of mass flow rate m dot h can be passed through a nozzle which has an area of 0.511. This means that I have to change these conditions. Okay. The only other quantity that I can play with is the turbine entry temperature. Right. This is the only other quantity that I can play with. So what we are saying now is, as the flight gains altitude, you are throttling back on the engine, which means you are reducing the fuel flow rate and the stagnation temperature at entry to the turbine. So we have to determine a value for T04 which is such that the area required, the mass flow rate is fixed at 51.69, right. So we have to find a stagnation temperature which will give me rho EH and AEH, which are such that when I substitute m dot h equal to 51.69, I get the area to be 0.511 meter square. Okay. Now we have to start changing thermodynamic properties. Okay. So let us summarize this. This is less than the desired value of 0.511 meter square. So what we need to do is adjust T04 to obtain rho EH and VEH which are such that an AEH of 0.511 meter square is required to pass m dot h, which is 51.69 kg per second. So when I change T04, my rho EH and VEH are both going to change. I have to keep changing, I have to keep iterating until I get a value of T04, which is such that when I plug it in here for this value of m dot h, I get the area to be 0.511. Okay. This has to be done iteratively, it cannot be done in one go. Okay. And if you iterate, then you have to do this couple of times. Let us see what happens. And you can already guess which way we are going to change the temperature. Are we going to increase T04 or decrease T04? We have to decrease T04, so that is understandable. So we decrease T04 to get, and again this is iterative. For the cruise condition, it turns out that a T04 of 1313.8, or let me just put it as 1314 Kelvin, is the desired value. For the cruise condition. So, if you do this, the thrust comes out to be, for after adjusting the T04 this way and the mass flow rate this way, the thrust comes out to be 16.8 kilonewton from the fan plus 10.4 kilonewton, I am sorry, 16 point, so this is the thrust fan. The fan thrust is 16.8 kilonewton plus 10.4 kilonewton, pressure thrust, momentum thrust and pressure thrust respectively, which gives me 27.2 kilonewtons of thrust from the fan, and the core engine is equal to 12.6 kilonewton plus 5.2 kilonewtons, which gives me 17.8 kilonewtons of thrust. So that the total thrust now comes out to be, I am going to erase this and substitute this value here, okay. So the total thrust comes out to be the sum of these two, which is 45 kilonewtons. Now we can see that the comparison with the manufacturer quoted value is much better, okay. Mass flow rate of fuel for this T04 works out to be about 0.945 kilogram per second. Instead of 2.94, this now becomes 0.945. Which then gives me a TSFC of 0.0756. We cannot expect better match of TSFC than this. Thrust can probably be matched reasonably well, but matching TSFC requires much more information about the engine, most of which is actually going to be proprietary information. So we really cannot get even more realistic predictions than this with the information that is available in the public domain. Now area of the cold nozzle 3.661, we have adjusted that. The area of the hot nozzle in this case actually comes out to be, I am sorry, area of the cold nozzle, now we have adjusted this to be 1.5 meter square. The area of the hot nozzle based on this procedure comes out to be 0.511 meter square. We have adjusted that also nicely. The mass flow rate through the engine has now been adjusted to be 274.48, and the stagnation temperature is now 1314. So you can see that our calculation procedure actually allows us to adjust conditions. It is able to not only predict values correctly for static conditions, but we are also able to adjust the thermodynamic quantities, the areas and other things for predicting thrust correctly under cruise conditions also. Okay, so the procedure is actually a very consistent procedure. What you must remember is that there are only two factors which are at our disposal. Remember, when we did this, we assumed that B, bypass ratio, is fixed, which is always going to be fixed. When you take off and then go to cruise, you are not going to change the bypass ratio, because the bypass ratio changes only with the diameter of the fan. That cannot be changed. We kept the fan pressure ratio also fixed, okay, which is reasonable. There are some engines which can actually operate with adjustable fan pressure ratios, but assuming fan pressure ratio to be fixed is a reasonably good assumption. We also assume that the pressure ratio is fixed across the compressor, which is usually a reasonable assumption to make also. Generally, the engines, engines are designed to operate at fixed values of pressure ratios and fan pressure ratios. They are usually not changed, although there are designs available which do that. These are reasonable things to assume. So the parameters that are available in the cycle are, as we said earlier, pressure ratio, turbine entry temperature, bypass ratio and fan pressure ratio. These are the four parameters. So we kept three of them constant. Only thing we changed was the turbine entry temperature, which gave us the kind of results that we were looking for. Mass flow rate can be adjusted without changing any of the thermodynamic property, values for the thermodynamic properties. That is what we did here. Okay. So the calculation procedure is very involved, but it is very powerful. Okay. It allows you to make very good predictions for both static as well as cruise conditions, and the exercise involves a lot of problems which are actually engines. These are engines which are in service today. So you can go through this calculations procedure for the problems given in the exercise, compare the values and then see how things go. Okay, are there any questions? Okay, so that actually concludes our objective of what we set out to do for aircraft engines. Okay, so turbofan engines and turbojet engines, we wanted to do thrust calculation and thrust specific fuel consumption calculation. So we have completed that. Now what we are going to see is, next is emerging trends in the industry for turbofan engines or commercial aviation engines. Then we will move on to ramjets and scramjets. So let us look at some of the emerging trends that are being seen in the commercial aviation industry today with respect to aircraft engines. We are not really talking about changes in fuselage or structures and so on, or aerodynamics. We are only looking at emerging trends in engine technology. That is what we have been talking about. So this is a little bit of a dated plot, but it is actually very revealing. The plot allows us to compare fuel economy of various modes of transportation, okay, starting from sports utility vehicle to passenger sedans, to aircraft, to high-speed trains and intercity trains. This is probably not a graphic that one would like to present when teaching a course on aircraft engines, because this shows aircraft engines in a very poor light in terms of fuel economy for number of passenger miles. Okay, so you can see that aircraft actually are better than sport utility vehicles. So aircraft lie here. The most efficient aircraft is expected to lie perhaps over here. Okay, this is a concept plane that is being studied, ultra efficient engine technology airplane. Okay, so this is located over here. But you can see passenger trains, which transport a lot of people, have probably the best fuel economy curve. Okay, this is at a load factor of 70, and if you think about typical Indian trains, they carry approximately 1,700 passengers or more per train. So the load factors for trains in India, express trains in India, will be close to 100%, if not more than that. If you discount people traveling on the roofs and things like that, the load factor will be about 100 for the Indian train. So in terms of fuel economy and emissions, probably the gold standard will always be passenger trains or express trains. Okay, so the airline industry probably should do a lot to meet these types of goals and standards. So what we are going to do in this module is to see what kind of technologies are being attempted to bring this operating point closer to, or if not competitive to, passenger trains. Okay. So this is how the technology has been evolving over the years, starting from 1950s to about 2010. Then we moved to turbojet engines, and turbojet engines are not really very fuel efficient. Okay. The big advantage that they gave was that you could fly at high subsonic flight Mach numbers, but fuel economy was not one of the things that was proposed for turbojet engines. You must also bear in mind that in the 1950s and 1960s, price of oil was relatively very low. Oil was very cheap. So fuel economy was not a major concern in those days. Speed of flight was much more of a driving concern than fuel economy and cost of fuel. Okay? But today, as I said earlier, more than 50% of the operating cost of any airline in the world is fuel cost. So now fuel cost is the driver for the technology changes in the industry. Okay. So you can see from turbojet, we went to turbofan engines. These are the introductory low bypass turbofan engines, and as you can see from here, there is an improvement in the fuel economy and it kind of tapered out in the 1970s with low bypass turbofan engines. Then the high bypass turbofan engines were realized. Remember, it is not a big jump to go from turbojet to a low bypass turbofan engine, because a low bypass turbofan engine will have reasonably small fan diameters. It is not going to be a transonic fan. It is only when you increase the fan diameter that you run into the problems of transonic fans, and as the diameter increases, if you remember, we also said that we need to spin the fan down slower, otherwise the centrifugal stresses will be very high. So the higher bypass ratio engines bring in those kinds of challenges, transonic fans as well as differential speeds, multi-spool technology and so on. So the low bypass turbofan engines do not present such challenges. So it was relatively easy for the industry to migrate from turbojet to low bypass turbofan engine. But it took a while before they could migrate to high bypass turbofan engines. And we looked at these technological challenges and how they were overcome in our earlier lectures. So over the years, the high bypass turbofan engines technology relating to that has more or less stagnated, as you can see from here. This is a long span, okay? We are talking nearly 40 years. So the technology has matured and it has stalled. So no more gains in fuel economy or efficiency or emissions appear to be possible with the current technology, which means we are looking for a paradigm shift. If you will forgive me for using this cliche, we need a paradigm shift to realize bigger changes in fuel economy, and that paradigm shift appears to be the geared turbofan engine, which probably will be rolled out later this year. So that is the technology that will start flying in the skies later this year. Okay, this is a geared turbofan engine, and it is expected to give a big boost, about 15 to 20% savings in fuel, and considerable amount of reduction in noise also, in addition to other things. Of course, if you have a 15 to 20% reduction in fuel consumption, naturally you are going to reduce the amount of CO2 and amount of NOx. Okay? Cost will also go down. Operating cost will definitely go down if you have a 15 to 20% savings in fuel. That is what is being projected for the geared turbofan engine. Let us see what is being done now. So here is where the current technology is. This is the direct drive turbofan engine. By direct drive, what we mean is the fan is directly coupled to the turbine, and this is one of the key barriers that we discussed earlier, because the fan is directly coupled to the turbine, and the turbines have to be run at a certain minimum speed to keep the flow moving through the blade passages. We were forced to run the fan at a speed of 3000 RPM, which brought in its own challenges, centrifugal stresses, multi-spool technology, transonic fans. So those were the challenges which were brought about because these are direct drive turbofans. The fan is directly connected to the turbine, okay? And because the diameter is large and the fan speeds are also large, these fans typically operate with fan pressure ratios around 1.6 to 1.7. That is what we used in our calculations also just now, for the worked example, right? So this is the space in which direct drive turbofan engines operate with propulsive efficiency around 0.8 or so. And you will remember that we had a chart earlier which compared the various propulsion technologies, right? Starting from the propeller, which had a bypass ratio of infinity, to the pure turbojet, which had a bypass ratio of 0. And if you remember, we pointed out that the turbofan engine, the high bypass ratio turbofan engine, has an efficiency which is better than the peak efficiency of a propeller engine. Okay, so we are talking about efficiencies of the order of about 0.8 or so. But the biggest stumbling block in improving the efficiency further has to do with this direct drive. If you can allow the fan to spin at a lower speed, then the efficiency of the fan will increase even more. But in order to do that, you cannot have a direct fan anymore. So the technology now, the trend is to go to geared turbofan engine. So you place a gearbox between the fan and the high pressure and the low pressure turbine. So the gearbox allows the fan to run at a lesser speed and at its optimum efficiency point. So you can see increases in efficiency to about 0.85 or so. This may not mean much, an increase of 0.5 or 0.05, right? May not mean much, I mean it may not seem to be much, but in terms of fuel economy this can be quite a lot. And from a noise perspective also this can be quite a significant shift. We will look at that next, alright. Now the best technology as things stand today appears to be the counter rotating prop fans. We showed a picture of this in the early part of our lecture, you can go back and take a look at that. This is a technology that GE is pursuing. The geared turbofan is a technology that both Rolls-Royce and Pratt & Whitney, most notably Rolls-Royce also seems to be pursuing this technology. Okay. GE is pursuing the counter rotating prop fan technology, which supposedly has a efficiency, at least on paper, close to 0.95 or so. Very difficult to realize in practice, but that is where the GE is going. Okay. Now if you notice, you can see that as we spin down the fan, the pressure ratio at which you have to operate also goes down. Right? If you spin it down, the relative Mach number of the flow that approaches the fan blade goes down. So the fan can also operate at a lesser pressure ratio where its efficiency can be higher. So you can see that the pressure ratio goes this way, right? It is, the pressure ratio is decreasing this way. So here we are looking at benefits of the proposed technology. So this is where we are today, bypass ratio around 5 to 6 or so, and so if you take that as your baseline for noise, okay, here we are plotting on this axis, we are plotting noise benefit from the baseline perspective. Okay. So here we are talking about effective perceived noise level in decibels. Okay. So you can see that the current engine stands here with a geared turbofan. The projected improvement in fuel efficiency, we are looking at a fuel efficiency improvement of about 15 to 20% with an increased bypass ratio. Even with the same bypass ratio, you can realize substantial fuel savings. Okay. The counter rotating prop fan is supposed to give fuel efficiencies of about 25% or so, reduction in fuel efficiency of 25% or fuel flow rate of 25%, but there is appears to be well, there is not a noise benefit, but there is not a noise disadvantage either. It appears to have the same noise level as the current family of engines, but with a 25% improvement in fuel consumption. Okay, so this is where the industry is heading today in terms of propulsion technologies. Now, if you look at the geared turbofan itself, we are talking about two important metrics. One is noise, another one is fuel burn. This has to do with efficiency, this has to do with compliance with noise standards. So the blue line here is noise, pertains to noise, and the red line here pertains to variation in fuel burn with increasing fan size. Okay. So as you can see, the current family of turbofan engines sit over here. This is their operating point. Okay. And here, as we increase the fan size, we are going from a lower bypass ratio to a higher bypass ratio. And as you increase the bypass ratio, I can relax the fan pressure ratio. Remember, the fan nozzle, the thrust produced by the fan nozzle is dependent on two quantities. One is mass flow rate through the fan nozzle, the other one is the pressure rise across the fan. So generally what is done is, for fair comparison, as I increase the bypass ratio, we will decrease the fan pressure ratio, which improves the efficiency considerably. Right? So as you can see from here, the current technology, turbofan engine, in terms of fuel consumption, sits as the best point possible, the lowest point in this curve, which is why I said that this technology has matured and is very unlikely to see significant improvements in this technology. Even if you increase the bypass ratio, you can see that there is actually an increase in fuel consumption due to certain other issues, which we will talk about later. Okay. So the only way to improve fuel economy is to move away from this curve, jump from this curve to another curve. So this is the curve corresponding to geared turbofan engine. So you can see that geared turbofan engine, if you increase the bypass ratio, definitely we get a much higher fuel consumption benefit. If you operate at the same bypass ratio, even then you get a good amount of benefit in terms of fuel consumption. Okay. Noise may not improve significantly, but you get a good amount of improvement in terms of fuel consumption even if you operate with the current bypass ratio. Okay. Now, the green one here is supposed to be either the next generation gear turbofan or the prop fan. Okay. Next generation gear turbofan is supposed to address some of the issues with that you have when you increase the bypass ratio to such large values. Okay. Currently, the gear turbofan operating space is in this region of bypass ratios, about 10 to 11 or 12, which is the highest bypass ratio engines that are in service today. That is the design space that we are looking at for gear turbofan. Increasing the bypass ratio beyond that will require the industry to overcome certain other technology obstacles, which we will talk about. Okay. So, this is what we are talking about. This is why it makes sense to move to the gear turbofan that the industry is moving to today. It is driven by fuel economy, cost of fuel. Now, as you can see from here, if I increase, so what we are seeing on the y-axis here is the thrust to weight ratio. Remember, we said that thrust to weight is the critical requirement for an aircraft engine technology. Right? So, as you can see from here, as I increase the bypass ratio, with large bypass ratios, with about 10 to 12 that we are operating with today, we definitely get good thrust to weight metrics. But if you go to very large bypass ratios, that actually becomes a distinct disadvantage. We lose out. So, here we are looking at increment of thrust to weight. So, from the previous technology, when I go to small bypass ratio gear turbofan, I get some benefit. Medium bypass, about the same benefit. Large bypass ratio, I get good amount of benefit in thrust to weight, about 30% benefit in thrust to weight ratio. So, the same engine per unit weight, the same engine produces 30% more thrust with the gear turbofan for bypass ratios around 10 to 12. However, if I become greedy and go to very large bypass ratios, then the same engine for the same weight, it produces about 20% less thrust than the previous version. Okay, so, there are some significant technological obstacles that need to be overcome before we can migrate to very large bypass ratio engines with gear turbofans. The prop fan does not appear to have an issue here, but it has its own technological challenges. Okay, this is only for the gear turbofan engine. Okay, and you can see what happens when I increase the bypass ratio. So, as I increase the fan size from the baseline to a larger value, you can see that the very large bypass ratio engines, the nasal drag, because the frontal area increases so much, the nasal drag increases almost quadratically with fan diameter. Okay, so, you can see that the very large bypass engines have much higher frontal drag. So, the increase in thrust that you are realizing is being not only offset, but also being negated by the increase in the nasal drag. So, it is actually becoming a disadvantage. You are producing less thrust than before when you go from large bypass ratio to very large bypass ratio. And this slide summarizes very nicely the various trade-offs when you increase the bypass ratio. So, as I increase the bypass ratio from left to right, you can see that the thrust specific fuel consumption reduces, noise also reduces. However, the nasal drag continues to increase, weight increases, the structural difficulty, meaning integration of the engine with the airframe becomes more difficult. The very large bypass ratio engines cannot be mounted below the wing. So, they have to be mounted above the wing or on the tail or on the fuselage. That becomes a challenge in itself because the engine is much heavier than the large bypass ratio engines. Okay, so, that poses a lot of structural challenges. So, these are the disadvantages as I keep increasing the bypass ratio. These are the advantages. So, what we need is, this appears to be the sweet spot. This is where we would like to operate. So, improved technology will perhaps bring this rise down a little bit down, so that we can enjoy the same benefits even at higher bypass ratios. That is what we have to see. Okay. So, if this sweet spot could be shifted, let us say to the right, meaning this curve becomes shallow, then if it goes like this, then we will be in a good shape. So that is where the technology is trying to go. But right now what we will look at is what is going to be offered this year, later this year, that is the latest technology, and that is the geared turbofan by Pratt & Whitney. Okay. If you remember, let us just quickly go back and take a look at the motivation for doing this. This is a direct drive turbofan that we saw earlier, and we emphasize the fact that the fan has to run at speeds around 3000 rpm or more because it is directly coupled to the turbine. The turbine cannot run at speeds lower than this. We actually allowed different parts of the engine to run at different speeds, again for the same reason, because the fan was really quite large and the centrifugal stresses would have been very large. So we said that fan has to spin at a slow RPM, whereas the high pressure compressor has to spin at a much higher RPM. So then we segmented the engine and mounted them on different shafts, so that this ran at a very high speed, this ran at an intermediate speed, this could run at the lowest possible speed. But that was 40 years ago. The time has come to allow this to run at even slower speeds, right, which means that we still have the multi-spool technology, but now we place a gearbox between the fan and the turbine shaft, which will allow this to spin at an even lesser speed and be more efficient. As the speed reduces, the efficiency of the fan increases because the pressure ratio can be brought down. Right. So that is the motivation for the geared turbofan technology. But the biggest challenge was in realizing a gearbox which would work. As I mentioned some time ago, the amount of power that this gearbox has to transmit is of the order of about 30,000 horsepower. Okay, for a high bypass ratio turbofan engine, it's about 30,000 HP. So to design a gearbox which can transmit this power, be lightweight, should not add significantly to the weight, and also produce much less mechanical noise. Remember, if you are going to add a gearbox, mechanical noise is a major problem. So this is a major challenge in terms of tribology and gear design and strength and lightweight. So this is a challenge which Pratt & Whitney presumably has overcome. So they are utilizing a 5-planet gearbox with a gear ratio of 3, so which allows the speed to be stepped down by a factor of 3. So this has bypass ratios, as I said, in the high bypass ratio range, 9 to 12. Low pressure ratio fan, okay, low tip speed, because we have stepped it down by a factor of 3. We have stepped down the RPM by a factor of 3. The tip speed also go down by a factor of 3. So we don't need presumably the controlled diffusion airfoils. Very likely the tip speed may not even see supersonic relative Mach numbers. So double circular arc may itself be sufficient. So a lot of things become simple if you could realize this critical piece of technology. So that is what Pratt & Whitney is using today. So here you see the experimental engine being mounted on an aircraft, and this is being test flown as we speak today, and it has a noise advantage of reduction of 20 decibels in effective perceived noise, which is actually a lot. 20 decibel is actually quite a lot. As I said earlier, decibel scale is a logarithmic scale, and human ear has only a fidelity of plus minus 2 dB. However, if you reduce the noise by about 4 dB or 5 dB, 50% of the people would perceive that to be a 50%, or most of the people would perceive that to be a 50% reduction in noise. Remember, noise is a perceived quantity. So majority of the people would feel a 4 decibel reduction in noise to be a 50% reduction in noise, although their hearing itself only has a fidelity of plus minus 2 decibels, okay, because it is a logarithmic scale. So 20 dB is a big reduction in noise, okay, and fuel burn supposedly is around 15% or so, okay, because we have kept the bypass ratio the same as existing engines, high bypass ratio, not very high bypass ratio. You will see 20 to 25% reduction in fuel burn only when you go to very high bypass ratios. Okay. So, here we are staying with the high bypass ratio. So, there is a saving of about 15% in fuel burn. Well, 60% reduction in NOx for a 15% reduction in fuel burn does not seem to make sense unless there are some other things which have been done in the combustor. Okay. But a 15% reduction in fuel consumption will definitely reduce the amount of NOx and CO2 that you are producing, there is no doubt about that. So, this is what presumably will be offered, it is being test flown and this will be offered towards the end of the year. So, we should be able to see this in the skies probably towards the end of 2014 or beginning of 2015. Hopefully, that will make flying cheaper. Somehow I doubt it. Okay. So, we have seen the kind of things that are in the offering in the immediate future. What we are going to see next is how the benefits are going to be accomplished. There are two frontiers in which engine technology is evolving today. Okay. One is from the efficiency perspective. The other one is from compliance perspective. How do you comply better with emission norms and noise norms, right? That is the other perspective. So, the efficiency, more efficiency is being pursued in two different directions or two different fronts. One is better combustor design, because fuel economy is going to give better efficiency. That is one line of pursuit for improving the efficiency. The other line of pursuit is the weight reduction, produce more thrust per unit weight of engine. Now, the weight reduction target itself can be pursued in many different directions. Let us see better manufacturing practices. If you remember, we said that the compressor blades are mounted onto discs and the discs are mounted onto the shaft. Okay. Now, new manufacturing technologies allow the blade and the disc to be manufactured as one single piece, that is called a blisk. This is a blade plus a disc. Through better casting and manufacturing practices, we can now blades integral with the disc, which results in considerable weight advantage. Okay. So, there are improvements in better manufacturing which can result in weight reduction. Better aerodynamics of the compressor and turbines will definitely improve the weight perspective. If the same blade can do more, that means I can reduce the number of blades. If I can make the same blade stage do more, then the number of stages can be reduced. If I reduce the number of stages, then the number of blades also go down significantly, which can result in significant weight advantage. So, that is how we are pursuing better aerodynamics. What is being done in better aerodynamics of turbo machines? Number one, counter rotating blades. If you remember, we said that the stator blade does nothing but redirect the flow from one rotor stage to the next rotor stage. That is all it does. It is not doing anything more useful for me. Can I make it do something more useful? If I allow the stator blades to spin in the opposite direction to a rotor blade, then that can also participate in work interaction. So, if it is a compressor, I can transfer work to the blade because now that has become a rotor. So, I can cut down the number of stages by a factor of 2. So, the stator now is doing more for me. So, counter rotating blades is a technology that is currently being used in GE NX engines and other engines which are offered with the latest aircraft. So, the stator blades are now doing more. They are not only redirecting the flow, but they are also participating in work transfer. And fewer blades, as I said, if I am able to do better aerodynamics, I can reduce the number of blades, which can also reduce the weight for the engine. So, the weight reduction can be pursued through better manufacturing, better aerodynamics, and obviously lightweight materials. If I can make the materials lighter, then I can do better, I can lose the weight. What are some of the technologies that are being pursued? The fan blade and the fan case are now being manufactured with carbon fibers. Instead of the titanium that we talked about, now they are being made out of carbon fibers, which actually results in considerable, significant amount of weight reduction. And the compressor blades are being made out of low density titanium aluminide material. Okay, so this allows the weight to be reduced substantially. Even if you are able to reduce by 10%, considering the number of blades that are there in the engine, this can result in a significant weight advantage. Okay, so these are the frontiers in which improved efficiency is being sought in engine technology. In the next class, we will look at what is being done in terms of better meeting norms, right, compliance with norms, and then we will move on to the next module.